Okay. So three-phase transformer for that we have discussed three-phase rotating magnetic field. Okay. So what is the meaning of three-phase rotating magnetic field? You will have three windings, and this concept is completely useful in motor whenever there is AC motor. Okay. So you will have three windings. When you will have three winding, then you will give this kind of supply, AC supply, that will generate from three-phase alternator, three-phase generator. Inside three-phase generator, there are three different coils, and they will generate this kind of supply, and that supply fed to these three coils. When you give three-phase supply to these coils, in this phase, there will be the rotating magnetic field, and that rotating magnetic field comes into the picture because one phase has a maximum current, so one phase has a maximum flux, another two has a half of the flux and in opposite direction. One has a maximum, another two waveform has a half magnitude opposite to that first one. So that you will have flux going in this direction from this coil at that time, opposite half flux going in this way for the one coil and another coil in this way. And vectorially, if you add these three vectors, then you will get resultant in this direction. And that is 1.5 times the maximum flux. And at that instant, so here you can see that number 3 is there. At number 3, these things will happen. After some time, at number 4, number 5, okay, this will become maximum and this will become half of the maximum. So the resultant flux in this direction. After some time, this will become a maximum and this will become half of that. So the flux in this direction. So one by one time pass, you will have here a maximum flux, then there will be the maximum flux, and then there will be the maximum flux. So you can say indirectly that that flux, maximum flux, is rotating in this way. And whenever there is a flux rotating and the conductor is steady, so at that time those conductor will experience that the flux is cutting through the conductor perpendicularly. So whenever the flux cut the conductor perpendicularly, it will generate the EMF inside that. And whenever there is EMF, according to Faraday's law, then there will be the motion. It will experience a force because current carrying conductor has a magnetic field, another magnetic field rotating in this direction, two magnetic fields interact with each other, then you will have the force. In whatever direction magnetic field rotate, in the same direction, there will be the motion of the rotor. So rotating magnetic field in this direction, rotor will also rotate in this direction. If rotating magnetic field is in that direction, then rotor will also rotate in this direction, clockwise. So this is the whole idea behind three-phase supply. So right now we are going to deal with three-phase transformer. So this is the motor and then we will generate this.
Three-phase transformer working on DC current.
DC supply. No. We already discussed it.
Phase 1 is covered.
Two answers are there. If you give the DC supply, let's say here, okay, magnetic field will be there. Yes, magnetic field will be there. Is that changing?
No.
Changing magnetic field induced in secondary coil.
No.
It is not changing, so there will be no EMF. So only the current flowing in primary winding, okay, and there will be no back EMF also. So it will draw very large current and it will burn. If DC supply is there, but you do switching on and off continuously fast, then there will be the EMF, yes, because the first time will give change of the flux in this coil. So DC supply is there and someone asks you that it is work, the transformer will work, then you need to ask the question. DC supply is continuous for the long time or there is a switching pattern is there. If switching pattern is there, then it will work. Okay. Otherwise, in general, on DC supply, it will not work. Okay, so now we are going to deal with the three-phase transformer. You know that what happened when the single-phase transformer is there. Now we are going to connect same kind of the three winding in such a way that the flux will inside the core operate in such a way that you will get the better pressure. Now, three phases are better than the single phase. Why? Because all the motors working on the three-phase supply, so you need that. For long transmission line, you need to step up. For that, three-phase transformer needed, and for the step down purpose also we needed three-phase transformer. So three-phase transformer constructions are different, but one of them is something like this. Suppose you will have a core and you create core something like this. Right. So three winding must be there. So I will say that here is the one winding. Okay. Then here is another winding. And here is the another winding. And these three windings on the core, we call it R phase, Y phase, B phase. This is called phase. Phase means a single coil, single supply, single phase supply. That means there will be the one coil. This is a single phase supply. Here. Because it is come out between this single coil two terminal. Okay. If three phase comes, then there will be the three points. Okay. For one coil, you need 2 points, phase and neutral. If three phase is there, then you will need. Yes, there is six terminals are there, but they are not 6 when you want to make the connection, because this coil, that coil, and that coil terminal. After that, the neutral will be common, so that will become one. So 3 phase and 1 neutral. If you connect them in a delta fashion, this is called star. If you connect them in a delta fashion, then it will have a 3 terminal. Now, how would you connect this coil, that I will represent later. But right now, you just understand what is 3 phase winding. Okay. So here I have a R coil. So I call terminal R dash. Here Y, so I will call Y dash. Okay, and then B. So B dash. Let's say R, Y, B are the phase, dash are the neutral. And this is the input or a one winding. And then secondary winding is mounted on the same core, let's say, then it will look like this. Okay, so we call primary side is a 1, let's say, when all the things are 1. And secondary side is a 2, then this will be R, phase R, but R2 and R2 dash. And this one will be Y1, and this one will be the Y2, so Y2 dash, and B2 and B2 dash. Okay. And when you apply 3-phase terminal, this kind of a supply through the R coil, Y coil and B coil, then you will current through these 3 coils in also same. And because of that, it will induce flux, generate the flux also in that area. So now what will happen? Flux is coming out of the coil, this white color. Okay, so current in this direction, it is coming out in this way. So flux going in that direction, and that will be the maximum of direction. At the same time, half of the magnitude flux going into the opposite direction. So here it will half of the magnitude in this direction and half of the magnitude in this direction. That is the flux. So previously 3 coils are spaced, and then we give the 3-phase supply. And right now 3 coils are there mounted on the core. And now they supply flux to the core. So what will the complete path? This maximum flux will go in this way. It divided into the 2 paths, 1 half here, 1 half there, and then they will come here. They will add it and come Next time this will become a maximum. At that time this B2 be the half and in the downward direction. So flux going in that way divided into the two parts, one going in this, another going in that way. They both come here, collected and distributed. Then this will become a maximum. At that time this will become a half. After that this will become in negative direction. So at that time this will be the half and in the opposite direction. So fluxing also going this way. So this kind of the 6 combinations are there, and those 6 combinations continuously doing their work. And how that happens continuously? You go in time from here to there. You go in time, each and every time you will have someone maximum, someone at the half. You go, we are understanding purpose, we are jumping from this point to that point. We skip this program, but actually this is continuous. And continuously smooth flux changing in such a way that always supply and demand will be balanced. Okay. Flux, one coil give the flux, another 2 coil will take the flux. So one coil is the source of the flux, another 2 coils are sink of the flux. So one coil will generate changing flux, another 2 coil will link with the changing flux, then this yellow coil will create EMF according to Faraday's law. Because 3 coils core will have a changing magnetic flux. So all the coil has back EMF E1 and all the yellow coil has secondary EMF. Okay. So in this way, whatever the changing pattern given to the transformer, yellow secondary coil will give you back. And if yellow coil has a higher turns, you will have a higher voltage with the same pattern. If this will have a lower turns, then you will have a smaller amount of the voltage with the same pattern. Now how we would represent this? Suppose this is the single phase, symbolically represented R dash 1 single phase. Okay. Then another coil, then another coil, 3 coils are there. Now I would like to connect this in a 3 phase with the 2 patterns. So 2 patterns are there for connection of the 3 phase supply. So one is something like this. Ground. Okay. Here is the ground. This one R dash. Then another coil from here. Ground. Okay. And the third coil will be here. Okay. So this is R1. This one is R1 dash. This is B1. Here is the B1 dash. Then, RY. And then B. Sequence will be RY, B. Remember it, okay? B1, and here is the B1 dash. Clear? And now I will connect all the ground in this way. This 3 point, it is called common point, and that is what we call neutral. Okay? A neutral terminal coming out in this way, or sometimes it is represented by ground. Something like that. Okay. So this is the idea R, Y, B. This is the first winding, this is the second, this is the third. For transformer, same diagram. For motor, same diagram. For generator, same diagram. Okay. And this kind of the connection we call star connection, because it looks like a star. And sometimes it is represented by Y. Okay? Y or star. Then after we will have delta connection. So now how do I get the delta connection? Another way of representing the star connection. See, star connection does not mean that it looks like a star. It may be connected in this way. That is the meaning of star. If the connection in this way, this is the one coil, okay, this is the second coil, this is the third coil, and if I connect all these three in this way and then give the supply, this is the star connected. 3 winding supply is there and all are connected. This is the star connection. So star connection does not mean that it looks like a star. We are oriented this cell in a star way so that it is easy to remember. Okay, so this is also star connection, this is also star connection. Okay, keep this in mind. Now we are going to talk about delta connection. So So I will have 3 coils R, Y, B. Okay. And what I am going to do, I will connect R1, R1 dash, Y1, Y1 dash, B1, B1 dash. I am going to connect R1 with Y1 dash in this way. Okay. Then Y1 with B1 dash. Okay. Then this terminal with that one. This is what we call delta connection. At where you need to give the supply to this 3 point. Connect this 3-phase supply with this 3 point. You need neutral? No. Only 3 wire are there. Here you need neutral. Connect 1, 2, 3 and another is the neutral. So sometimes neutrals is needed in star connection. If supply is balanced, what is the meaning of balanced? Balanced, that means this phase go perfectly 100 watt. All should go 100 watt. One way of balance. Another 360 degree wave is there. Then divide into the 3 part. That means 120 degree should be there. So one mesh, second mesh should start from 120, another for 240 from the 0. Or we can say from first, another will be 120, from second, third will be also 120. So third will be 240 left with respect to 1. Okay. So this is the things happens, then it is called balanced supply. It is perfectly balanced because each and every coil has a voltage which rise to the maximum value. And they are perfectly divided into the 3 parts in time. Then the things come is called balanced load. So when you give this kind of the supply, 3 phase, okay. So same way you can connect winding. So here is the 3-phase supply. Let's say on this side 3-phase supply is there. 3 wire comes here. So this thing is called supply. This is called load. Okay. And what is the meaning of balanced load? All the winding has the same impedance, or we can say resistance. 100 ohm is there, then 100 ohm and 100 ohm should be there. RL is there. Whatever the magnitude of resistance, whatever the magnitude of inductance, same should be in this winding and in this winding. Then and then we can say that the load is balanced. So what is the meaning of the 3-phase supply is balanced? Supply is balanced, that means voltage should be going perfect value and they have perfect phase balance. What is the 3-phase balanced load? Balanced load, that means it has all the ohmic load impedance should be same. So the whole picture is something like this. If you have a generator, if you have a transformer, if you have a motor, you can represent this way, 3-phase connection. So what I will do, I will represent something like this, that this is my generator. Okay. This is my generator. Then there will be the transformer. Okay. 3 wire comes in this way. I am not going to draw that, but they are connected here. This coil, that coil, and that coil. After that, 3 wire coming out from this here terminal. And then you will have 3-phase load. That's a motor. Then you are connecting this one. And this is the motor. This is the transformer. Complete picture. Okay. Balance supply, balance transmission, balance load. When load will become unbalanced, here is a more resistor, here is a less resistance. Okay. Then voltage will be same across all these coils, but current will flow difference. So at this terminal, extra current wants to come out. If the load is balanced, then whatever the current comes in, that is also divided in these 2 coils. But if it is not balanced, whatever current comes in, it will not going to be sync. So some of the voltage or current will be available at this terminal. This is called unbalanced load. Okay. And everything is balanced, then it is called balanced load. So do you have the idea of the balanced load and unbalanced load? 3-phase supply, 3-phase transmission, 3-phase generation. And this connection is what we call star connection. We are going to discuss delta connection a little bit later, but right now understand this is the star connection. Okay, so this is the generator, same symbol for the motor, same kind of the symbol. Okay, transformer we just give the coil, this kind of the coil. Okay.
સર
Yeah.
આપણા બેલેન્સ સપ્લાય કનેક્ટ કર્યો એની જગ્યાએ સર ત્રણેય કોઇલને પેરેલલમાં કનેક્ટ કરી નાખી દો.
ત્રણેય coil
આ વાઇન્ડિંગ મીન્સ છે આર વાય ને બી એને પેરેલલમાં કનેક્ટ કરી નાખી દો.
parallel, this is the parallel connection actually. Think about it. This is the parallel connection.
ડિવાઇડ થઈ ગયું.
Are you getting my point?
પછી
One coil, second coil, third coil. Terminal are there. Do you want to connect them parallel? Give supply here, give supply here, and give supply here.
દસ
And then make the combo. This is parallel. And this is in series. This connection is called delta and that connection is called star connection. Okay. Alright, so now we are going to draw.
સર એ પેરેલલમાં છે તો વોલ્ટેજ તો સેમ જ છે બરાબર.
Yes,
તો સર તો પછી એના બેલેન્સ સપ્લાય સાથે કેમ જોડવું?
voltage same, that means see, balance supply. The meaning is that when you give supply here, here and there, 3-phase simultaneously, this will become maximum, after that this will become maximum, after that this will become maximum. But this will become maximum 100, this will become maximum 100, after that time this should be become maximum 100. If it will become a 90, then there will be the fault, we can say. It is not good condition. Must be balanced that all the coil should go sinusoidally. 0 maximum, 0 negative maximum, 0. So another coil should also follow the same pattern after a little bit of time. So it will also go the same way as the first one. And third one will also go the same way as the second one. So if this going to the maximum 100 volt, then will also follow the 100 volt. But some problem is there and there will going to be only 90 volt. Then we cannot say that this is the balance. It is not balanced. So for the balanced condition should be required is 2. Maximum peak to peak voltage and another is the phase shift.
તો સર એ થર્ડ કોઇલને બેલેન્સ માટે આપણે નંબર ઓફ ટર્ન્સ ઇન્ક્રીઝ કરી દઈએ તો
Many things are there. Generation happens because it is a generator. If let's say it is a generator, then voltage coming out from the coil. So what happens if 90 volt is there? There will be the fault under that generator. Generator coil has a less number of turns. That pole has a faulty part, so that magnetic field not coming out properly. So if magnetic field is not properly, then whenever conductor go through that pole, it will not create a maximum voltage. Okay, so 1, 2 and 3 pole are there. Generator rotating like this, it will conductor going this way, cut the magnetic field maximum 100 volt. Going to the next, conductor cut the maximum 100 volt. Going in this part 90 volt. Some fault is there, magnetic field is weak. So we need to treat it, we need to correct it. But in generally, generator will always give you balance supply. Load is not balanced. Load is really unbalanced. They try to make the balance, but in general it is not balanced. One phase goes to the society 1, another phase goes to the society 2. One society has a 50 ohm, another society has a 100 ohm. 100 people will switch on the light, 50 ohms will switch on the light, then there will be the very difference. Okay. So R1 dash, R1 dash, B1 dash. Okay. From R1, you are going to the R1 dash. Here is the wire. Okay. Two way we can connect this connection. This is the one way. Another way supply here R1 dash. It is terminating point. Connect with the wire. Y1 going to the Y1 dash already there. Connect to the B1 and then it will go like this. And then take the terminal from here and from here. And another terminal going back to this coil. So 3 windings are connected in series and 3 terminal coming out. So you can connect this terminal to that winding also, and then this terminal to that winding, and then this terminal will be here. Also this is we can say in the series or also you can connect in this way. So here if I will change, then it will look like this. R1 dash, it will go in here, then it will go in here, and then it will come in back to the first. So you need to follow the pattern. If one going this way diagonally, then first one going this way diagonally, third one going this way diagonally. Okay. If you want to connect from here to first, then this one will go diagonally, then this one will go diagonally, and that one will go here diagonally. Okay. So this is the way that you can connect a delta winding. Both ways it is possible. Alright. So now I am going to draw the delta connection. So what will happen with the delta? That suppose I will have 3 coils are there. Okay. I am going to connect in this way, 3 coils. Alright, let's say this is the first coil, then it will be the R1 dash. Then second coil is B1 dash. Then third coil, sorry, it's a Y. And then third coil RYB, B1 dash. Okay, and take out 3 terminals from common point. So now I want to draw the same connection here in this way. Okay. So this is R1 dash, Y1 dash, B1 dash. Okay. So see, R1 dash connected to the Y1. So R1 dash connected to the Y1. Y1 dash already connected. Y1 dash connect to the B1. Then connect to the B1. B1 dash already connected. B1 dash to the R1. B1 dash to the R1. And then take common terminal R1 dash Y1. R1 dash Y1. This one. Common terminal. Y1 dash B1. Y1 dash B1. This two terminals take common here. B1 dash R1. B1 dash R1 take common terminal from here. You can take from here, anywhere. Okay. So these 3 terminals are coming out. So this kind of the thing we call as a delta connection. And we replace it by this symbol. So 2 possible connections are there for 3 coils. One is a star way, another is a delta way. When you give the supply here, then the things getting little bit different. Now what is the difference that we are going to discuss now? It is called transformer connection. Okay. So this is for the delta. And I am going to draw another winding for the star so that you will have an idea. R1 dash, Y1 dash, B1 dash. Okay. So for the star, connect all these 3 things together, make it ground, and give supply here. Comfortable? This is the star. You draw this drawing also, and then this one. Then draw delta connection. This drawing also, and that drawing also. Okay? Draw it. To draw the phasor diagram, we know that phasor diagram is nothing but the vector diagram, and that vector diagram is rotating anti-clockwise. That is the meaning of phasor. If I have here a vector, let's say vector A, okay, and that vector start to rotating, then we call it a phasor. Okay. So what we are going to do, we have here three phase supply. So for star connection, here is the neutral. So one voltage source here, another voltage source here and there, another voltage source with this winding. So whatever the voltage here applied in between these two terminals, actually that is the voltage appearing on this winding. Whatever the voltage applied between this terminal and that terminal, that will be the voltage that is going in this way, from this winding.
Sir, now check phase angle 120 degrees.
Yes, 120. Whatever the voltage that we are going to apply here is V1 and ground, that will be going this way. Okay. So this is in this way, all the three winding will be the under pressure of the voltage, and that voltage is called a phase voltage. So first thing we are going to write down phase voltage, and then we will represent it by V, and then we will write down PH. That is what the phase voltage. Then, if I will apply voltage between these two terminals, then that will be the voltage across this winding, and that will be the voltage across this winding. Okay. So here is a line, this is the line, and this is the line. This is the phase, and phase. If I will apply the voltage between these two lines, then it will call the line voltage between R1 and Y1. Then if I will apply voltage between these two lines, then that voltage will go through this phase, and that voltage go through this phase. So these two windings are in series if we apply between these two terminals, and that is called line voltage. Then third condition, that I will apply voltage between this terminal and that terminal. At that time the voltage will cover this winding and that winding. Okay. So when I apply the voltage between phase and neutral, then that voltage is completely across every other phase. But if I will apply the voltage between not phase and neutral, but phase to phase, this phase to that phase, this phase to that phase, then it will what we call line voltage. So here is the line voltage, line voltage, line voltage. What is the phase voltage? Voltage between this winding, voltage between this two winding, voltage between this two winding is called phase voltage. So this is the main two terminology. There is line voltage, or sometimes called phase to phase. So it will be represented by VL, or sometimes V phase, V phase. But we are not going to use this. We only consider these two symbols, line voltage and phase voltage. Clear? This terminology you must have clear. If I say what is the phase voltage for the R winding, then you have to consider this winding R, and whatever the voltage across this two terminal, and that voltage is ultimately going this way and here to ground, 0. Then and then that will be the voltage between this one. If I told you what is the line voltage between R and Y, then you need to consider this voltage, because those two voltages ultimately going in this way. Okay, at that time it will not go through the neutral way, it will go in this way, because this is the source and half of the portion will be the sink. Okay. Alright, so this is the phase voltage and line voltage. So I am going to do now is that phase voltage here, phase voltage here, and phase voltage here. And what is the line voltage? This is the line voltage between R and Y. So I can write down this way also, or I can write down in this way also, VL. Then between this winding to this winding, VBR. Not RB, because we have to follow the sequence. RY, YB, and then BR. Okay, it is also a line voltage, and then voltage between these two terminals, that is RYYB. This is also line voltage. Phase voltage for the R, so we call it VR. Phase for the Y, so we call it VR. Phase for the D, so we call it VB. Okay, same terminology. Phase voltage, line voltage. Three pairs are there. Okay, so 120 degree apart phase voltage. Let's take start from the phase voltage VR. So I am going to draw here a phasor VR. This is our ground, our reference. Okay, VR. See the phasor, and it has a magnitude and it has a direction. This is the magnitude and that is the direction. Okay. After that, VR, VY, Y will comes into the picture. Okay, and phasor diagram what is in this side. So VY will come in this direction 120 degree. So here is a 90 degree. Okay, here is another 90 degree. So 90 plus 30 in this direction, approximately same magnitude in this way. VR, VY. Sorry, VY will come in this way. 90 plus 30. VR, VY. Why? Because when this whole structure rotates in this direction, first come VR, then comes VY, and after that it will come VB. Okay. So after 120 degree VY is there, after another 120 degree VB is there. Okay. So you can see that 120 degree delay VY and 120 degree forward VB. This is ahead, leading vector to this one, and this is the lagging vector through this one. So I can represent in this way that this is a 120 degree. This is also 120 degree, and this is also 120 degree. All the three phasors have relative 120 degree. Okay, check it and think about it like this relation. Going in this direction, rotate the structure at this point in this direction. Then starting from here, if here is the person, then what he will see? He will see first VR, then he will see VY. After 120 degree, he will see VB. VR, VY, VB. Okay. Now I want to draw line voltage in this phasor diagram. So what should I do? We know that voltage between this phase and that phase. So it is actually the voltage difference. Voltage between these two terminals, it is actually voltage difference. Voltage between these two terminals is actually voltage difference. So I need to take a voltage difference between R1 and Y. So this is the VR, this is the VY, this is the VB. R and Y. I want to take a voltage between R and Y difference. If I directly add these two phases by law of parallelogram, then I will get the addition. But what I need difference. So what should I do? I need to flip one vector 180 degree. 180 degree I need to flip the vector. So if I flip the vector, then vector will become negative. Let's say I flip the y vector in this direction, then it will become a negative Vy. And then I will add these two vector, then this addition is nothing but the difference of the Vr and Vy. Are you getting this point? Alright. So now I am going to flip the vector Vy. And the key thing is that these all vectors are same magnitude. Okay, magnitude is same. So I can represent with V. Okay. So let's flip this vector on the
magnitude में sign change नहीं है
magnitude will be same, sign will be changed. So this one is the negative, approximately negative Vy. what is the angle between yellow vector negative Vy and this vector? 60. How can you find it? Because in this two vector there will be the 120 degree. And this is also in middle between these two vectors, because this whole circle divided into the equal three parts. And all these magnitude vectors are same. Okay? Because peak is same. So magnitude must be same. In a 120 degree it is divided into the three parts. So here is a 360 degree, it should be divided into the three parts. Going in this way, this is 60 degree. Now I need to add this by log error term. This way and another in this way. Then this one will be the resultant from here to there. And this is VRY. Because R is positive, so we write down R first, Y is negative, so later on the Y. If I say VYR, then it is Vy minus VR here. That is the sequence, that is the concept that you need to follow. Now I will ask you the question that what is this angle? Between white and pink vector.
VR minus VRY.
Angle. This angle is 180 degree. Then between these two, 60. And now between these two, 30. How can you say that? Because this two vector has a 60 degree angle and magnitude is same. So resultant exactly comes into the middle. If some vector is larger than the another one, then the resultant vector will go in this way or that way. But two vectors have same magnitude, because this is the same as this one VR. So we take equal and opposite. So I can also put two arrow here. It is same. Then the resultant will come out, will exactly between the center of the corner, center of the angle. And the key thing is that what is the magnitude? Okay. So magnitude for the VRY, we will apply this rule, VRY square. Vector addition. VRY square is VR square. Negative Vy square, that means Vy square. Okay?
2 Vy. VR.
Take only magnitude. 2 Vr and Vy. Do not consider this sign right now. Why? Because we want just addition. So if 5 is there, because we know this is negative, that is indicated that it will come here to there. Otherwise, this is also magnitude and that is also magnitude. So consider only magnitude 2, Vr, Vy, cos angle between these two, 60. Okay. But VR, Vy and Vb all are phase voltage. Okay. Phase VR, that is same is phase Vy and that is same as phase Vb. Okay. And all the phase voltage we call V phase and all are the same. So let's call them V phase. Common magnitude. So I will call here a V phase square, V phase square plus 2 times V phase square, then cos 60, sin 30, 1 by 2. Okay? And VRY, RY, YB, BR, we called it line. Okay? So I will write down here. VRY is the same that comes later. VYB and VBR is line to line voltage or line voltage VL. Okay. So we call this RY square as a VL square. Okay. So this 2 and that 2 will cancel. So 1, 2, 3, it will become 3 times V phase square because it is a 3-phase system. But when we take a square root, then we will get VL is equal to under root 3 So I give you last time example that if you have two vector and they are in 90 degree and same magnitude, then you will get root 2 times this magnitude, 90 degree. If you have a 60 degree, you will get root 3 times. If you have a 120 degree, you will get same as this one. These are the special case of the vector. So VL is root 3 times V phase. This one is root 3 times VR or Vy or Vb because all the things are same. So this vector is root 3 times R. Okay. And from this I can check that line voltage. If I apply the voltage between line to line. So line voltage is leading then the respective phase voltage by 30 degree. Line voltage RY leading with the phase voltage VR by 30 degree. Okay. Same way, if I told you to go for VRY, VYB, then what you will do? YB. You flip this vector in this direction, it will become negative B. And then add this vector and that vector resultant will be here. Then BR, YB, then BR, flip the R. So flip the R here, add with the B, you will get resultant here. So one another pink vector will come here and another pink vector will come here. And that is called the complete phasor diagram. But we are running out of the space, so you just draw this and write down this relation. And yes, before that, one more thing, and that is current going in this line here. The same current that going into the line also go into the phase. Same current that going in this line also go to this line. Same current going in this line also go to this phase. So phase current IR and the line voltage is same. But the line current and phase current are going to be same. But line voltage and phase voltage has this relation. And line voltage considered two winding, so that voltage must be higher than this phase voltage. So see, line voltage is higher than phase voltage by root 3 times. Okay, and line current and phase current is same. So also mentioned here that for the star winding, IL must be same as I phase for all three phases.
According to KVL. No.
Yes. And then after you can apply here the KVL. And that KVL must be, not KVL, KC, current,
Kirchhoff current law.
But when you do algebraic sum at this point, you will find the answer 0. Because whatever current comes is half of that going this way, half of that going in this way. Same happen with the voltage, same happen with the current, same happen with the flux. Write it down. Negative B. Then I need to add Y and B. Y, B, positive first, negative then. Later, V, Y, B. Then it will come BR. So I need to shift R in this direction. Negative BR. I need to add them. BR. Okay. In your book, this letter will be bold. But when you write down with the pen paper, then you would need to put a vector here. If you want to replace a vector, you have to put the arrow, you have to put the bar. You can put also here curly little, like this curly symbol, or you have to draw dark bold symbol. So this is hard. So whenever you write down something, you need to use one of this kind of notation. Okay. Alright. So this is the complete phasor diagram. Now tell me, what is the phase angle between all three line voltage? VR, VY, VB.
120.
How can you say that?
स्टार लाइट से सिवाय टोटल तो 360 करेंगे.
Here is the third ring between this line and that line. After that, between this line and that line, 90 degrees already there. 90 plus 30 is 120. And same thing happened with here and here. So line to line is also 120 degree. Face to face is also 120 degree. Now we are going to deal with phasor diagram for delta connection. For delta connection, so here I will again represent these things V, R, Y, then V. Okay, no need to represent these things. Then we will represent later on. What are these voltages? Okay. So tell me, what is the voltage relation between phase voltage and line voltage? This is my line voltage. This is also line voltage. This is also a line voltage. This is phase voltage, phase voltage, phase voltage. This is R winding. This is Y winding. This is B winding. Take R phase. Do you get the question? What is the relation between line voltage and phase voltage? In star winding, this is the relation. VL is equal to root 3 V phase. What is the relation here between phase voltage and line voltage?
Root 2. VL is equal to root 2 into VPH.
How can you say that? Right, is equals to the same. She's right. See, it is voltmeter here and there. Whatever the voltage here, it will be same here, 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 here.
No, parallel.
Okay, so this is directly parallelly given to this winding. This line directly parallelly given to this winding, and this line directly parallelly given to this winding. And then connect all three windings. Okay, so in delta, V phase is equals to V line. But current is not same. Here is the current, line current. Okay, here flowing the current in this way, let's say IR. In this way, ID, and in that way, IY. IR, IY, ID, IY. So I am going this way, then at this junction, IR plus IY something happens. Or we can say IY, then IR and I. Something like this combination happens at this junction. So current is not same. In the star connection, current is directly going in this way. Going in the line, directly drawn into the phase. But in delta, current is different, voltage is same. But it is turned out that when you draw the vector, then you will get the same kind of relation, that IR is equal to root 3 times I phase. So whatever the relation, and in the star, IL is equal to I phase. In star, here in delta, this is the relation. Okay, so let's plot on the phasor diagram. Here I have a current vector, because we know that the voltage is same, so we do not draw the diagram. If I want that diagram, then this will look like this. VR, which is equal to line voltage, VY is equal to line voltage, B is equal to line voltage, RYB all are same, and angle is 120 degree. connection voltage. Now we are going to add the phasor diagram for delta connection current. So first I will draw here phase current IR, because we know that these are the winding, and three-phase current also follow the same pattern, maximum magnitude and 120 degree apart. So here IR, somewhere here IY, and in this direction RYB. Okay, and all those vectors are same, and all have a 120 degree relation. Now we want to add two current. So one going away and another comes in. If you want to make that another is also going away, then draw the opposite diagram, opposite vector. Okay. So whatever the vector here, I, Y and I R, make one of them opposite. Let's make this Y opposite. So I need to flip that vector here also in this direction. And that will become negative I by. And at this point, add vectorially two current. So I will add those two currents. And then get the resultant. Okay, and that is the line current. But what is named RY? And same thing, what is the angle? 60 degree. What is the angle? 30 degree. What is the magnitude? IL is equal to root 3 times I phase. Phase I will represent with H. Okay, and you can add this by the equation that we have done previously. I am not going to write it down again. Okay, you can understand. Replace all the V with the I. Same way you can also draw here. I am drawing again so that you will become a little bit familiar. IB in this direction, negative IB, add them, that will become YB, so IYB line current, and split this R vector in this direction, okay. Then add this way and add that way. Minus PR, sorry IR, then it will become DR, not I. It is like okay, current, put I on everywhere. And this is the phasor diagram, and that will be the relation. IL is equal to root 3 I phase. Okay. So this is how you need to represent voltage and current phasor diagram in star and delta phase. In star, if voltage is unbalanced, then at neutral point some extra voltage appears. In delta, if current is unbalanced, then some amount of the current will circulate in this winding. Because whatever comes in, it will match this direction and that direction. If it does not happen, then some of the current will remain in this loop and it will continuously circulate. So you cannot measure that by putting ammeter here, here or there. You need to put ammeter here, here and here. And then you need to check that if that is happening, if not happening, then it means some extra current is circulating inside the winding. So in electrical engineering, some concept is there called harmonics. It will set the current out of phase in such a way that there will be circulating current and it will hit the winding. You measure current 5 ampere here, but it is happened that the addition of this two current is not the 5 but 6 or 7. So extra current will be circulating in this winding. Okay, so write it down here.